In this video, we're going to look at the greenhouse effect and its effect on the balance of energy here at the surface of the Earth. So what we've seen is that the sun emits shortwave radiation, that's wavelengths of radiation with very, very short wavelengths, specifically visible light. And then we've also looked at the Earth, which is emitting long wave radiation, radiation with longer wavelengths, particularly infrared is the wavelength that the Earth emits. Earth is simultaneously receiving the sun's shortwave radiation and emitting the long wave radiation, doing both of these at the same time. Now, just like this balance we've kind of talked about in past videos, this has a balance as well. If we receive more radiation than what we emit, then we end up gaining energy. And what happens to the temperature if we gain energy? Temperature is a measure of energy, so more energy means higher temperatures. And this is very common in during the regular daytime cycle. As the sun rises, you start to receive more energy than what you emit, and as a result, it gets warmer and warmer through the day. But what if we receive less than what we emit? For example, in the evening or in the middle of the night, we're not receiving much radiation at all in the middle of the night, but we're still emitting radiation all hours of the day, even in the middle of the night. So we're emitting more than we're gaining, so we end up losing energy. And what happens to our temperature if we lose energy? Well, again, temperature is a measure of energy, so less energy means lower temperatures. But if the amount of energy that we receive is the same as what we emit, then there is no change in energy. And in this case, since the energy doesn't change, the temperature doesn't change either. This is what we call radiative equilibrium temperature, the temperature at which the energy that we emit perfectly balances the energy we are receiving. Okay, so what about nighttime when there is no incoming shortwave radiation? Well, in theory, all of our radiation just goes off into space and it gets really cold. In fact, if you go to the surface of the moon, daytime temperatures are something like 250 degrees Fahrenheit, whereas nighttime temperatures on the moon are negative 150 degrees Fahrenheit. Few variables that play into this, but the question still stands, why doesn't it get that cold on Earth when our nighttime side emits radiation? Well, the answer to that is that there are actually three players in this equilibrium. We've only talked about two. The first is the shortwave radiation incoming from the sun, the outgoing radiation from the Earth's surface, and then the third player is actually the Earth's atmosphere itself. So the sun and the Earth act like a black body. That's what we've been talking about the last couple of videos. We've talked about how it has that nice gentle curve with a peak wavelength based on the temperature and the amount of radiation based on the temperature, so on. The sun and Earth act very, very close to a black body. However, the atmosphere does not. The atmosphere has what we call selective absorbers. They're objects that selectively absorb and emit radiation at particular wavelengths. The figure on the right here shows a number of gases in our atmosphere. For example, the very top one, this figure is in your textbook, so you can look this one up as well. The top figure talks about nitrous oxide, N2O. Very good at absorbing radiation that, sorry, I'm getting my laser pointer here. There we go. Very good at absorbing radiation about 5 micrometers, and that's about 7.5 micrometers there. Very good at absorbing radiation in those particular wavelengths. Methane, really good at absorbing radiation at 4 micrometers, and again at 7 micrometers. Ozone, very good at absorbing ultraviolet radiation. Then ozone and oxygen are also very good at absorbing radiation, right around 10 micrometers. Now, an important note here is what we call Kirchhoff's law. And that is that materials which are strong absorbers at a particular wavelength are also strong emitters at that wavelength. So if you have methane, which is really good at absorbing radiation at 4 micrometers, it will absorb that radiation and then it will re-emit that radiation at 4 micrometers. Okay? And the thing is that with the atmosphere kind of higher up, Earth radiates energy up, it absorbs that radiation. The methane will absorb that radiation, and then it will re-emit that radiation in all directions, including back at the surface of the Earth. Come back to that in just a second. But let's finish up with this figure because there are a couple of very important points here. Now, this figure is not an exhaustive list of all the molecules in our atmosphere. Just some of the more prevalent ones: nitrous oxide, methane, oxygen, ozone. Water vapor is very good at absorbing long wave infrared radiation, as well as some of the shortwave infrared radiation. Carbon dioxide, very good at absorbing long wave radiation. When you put them all together, then you get this figure at the bottom. This is the total atmosphere. The atmosphere is very good at absorbing ultraviolet, thanks to the ozone. It's very, very little absorption in the visible spectrum. That's why visible light can pass through, and we can actually see the visible light from the sun. The atmosphere is also pretty good at absorbing most infrared radiation between 1 micrometer and about 7 micrometers, and then also really good at absorbing radiation above 12 micrometers. But this gap between 7 and 12 micrometers, there's kind of a hole there. And that's what we call an atmospheric window. So there are two obvious holes here. One in the visible spectrum and one in the infrared spectrum, which happens to be right about the wavelength at which the Earth emits radiation. This is important. We'll come back to that in just a second. But what does this mean for our atmosphere? With Kirchhoff's laws, meaning that some molecules are really good at absorbing particular wavelengths, they will re-emit radiation at those same wavelengths. It means that we now have something to trap the energy in our atmosphere. So, figures on the right, on the top, you have the idea of the Earth without greenhouse gases. Incoming solar radiation hits the surface of the Earth, we absorb it, and then you have outgoing infrared energy goes out into space. We lose it. End of story. And if the sun sets, then all we're doing is emitting radiation, and that energy leaves, and we get very, very cold. But the figure on the bottom shows what happens if you have an atmosphere. The sun emits radiation, comes and hits the Earth. We absorb it, we warm up, and we emit infrared energy. A lot of that infrared energy makes it out into space. But some of that infrared energy is absorbed into the atmosphere by the molecules or greenhouse gases that make up our atmosphere. Once that energy is absorbed, it will be re-emitted. Some of it will go out into space, and some of it will go back to the surface of the Earth. Now, there's a very great example of this, and that would be, say, a carport. If you leave a car outside on a winter's night, outside of the carport, and another car inside the carport, the car outside of your carport would very likely have frost on the windshield in the morning. And that's because it's just losing its radiation out to space. There's not really anything to trap the radiation in, except for the atmosphere itself. But the car inside the carport will radiate energy up, and that energy will be absorbed by the roof overhead. Then the energy will be radiated back down, keeping the car warm enough so that you don't have frost. So you have one car outside, out in the open, as if we didn't have an atmosphere or anything to cover us. It radiates energy away and it gets super cold. With the car inside the carport, just like us here on Earth with the atmosphere above us, the radiation from the atmosphere, roof of the carport, will re-radiate energy back down, keeping us warm. So, greenhouse effect works like this. The Earth emits long-wave radiation towards space. Greenhouse gases in the atmosphere absorb some of that long-wave radiation and then re-emits the long-wave radiation back to the surface of the Earth. Now, this is great, except for when the balance is off and the atmosphere re-emits more energy than what we emit, in which case the temperatures would stay extremely warm. So you remember those two gaps we saw in this in our atmospheric profile here? This is where that comes into play. We have a visible window, which is very good because this allows sunlight to reach the Earth's surface and to warm us up. But if greenhouse gases kept all that energy in, we would overheat. But it turns out that the atmosphere is made in just a way that we don't have a whole lot of absorption here in the atmospheric window in these particular wavelengths between 7 micrometers and 12 micrometers. This atmospheric window basically means that we can take our most intense radiation and it escapes out into space. But these other wavelengths, which the Earth is giving off, gets trapped and re-emitted back to the Earth. Same with these shorter wavelengths over here. And it's just the right amount of energy to keep us warm overnight. So the atmospheric window is essentially a safety valve, keep us from overheating here at the Earth's surface. So here we go. We've got the full picture now. We can see the full picture of how our atmosphere is heated. It starts off with solar radiation coming in and heating up the surface of the Earth. And then you have a little bit of conduction, which heats up the air just above the ground. And then it becomes more buoyant and starts to move upward, and you've got yourself a convection cycle. This is where your clouds and your storms start to form. But to maintain that balance of energy, the Earth is going to be radiating some energy out to space, as well as some energy out into the atmosphere, which re-emits back to the surface of the Earth, essentially acting as a blanket at nighttime, making sure that we're not too cold. If we don't maintain that radiative equilibrium, if we do maintain the radiative equilibrium, temperature doesn't change. If we have more energy coming in than what we radiate out, we have a surplus of energy and we warm up. And if we have more energy escape than what comes in, then we have a deficit of energy and we cool down. And there's going to be a balance between these. That's going to be the topic of our next lecture. And one thing that we'll see is we're talking about a radiative equilibrium or a balance in radiation. But the key to keeping this balanced is actually weather, the whole principle of conduction and convection in our atmosphere. And this is what will keep us very well balanced, so that our temperature doesn't become too extreme one way or another. Next video, we'll talk about that balance known as the energy budget.